Hi, welcome to Calculus 2 lecture series. And we are in the unit number 4. This is a very long unit. We talk about the sequence and the series. This is our lecture number 20. In this lecture, we're going to talk about the ratio and the root test to test to see if a series is convergent or divergent. We're going to have 2 videos for this lecture. So the first video, we're going to talk about the ratio test. And the second video, we're going to talk about the root test here. All right, so now let's go ahead and go to our lecture notes here. Okay, so what is the ratio test here? Okay, so for a series, if the summation ANs, right? So we talk about a series is n from 1 to infinity the AN. So the ratio test here, we have 3 criteria here. The first thing here is if the limit n approach to infinity. So if you have the an plus 1 over an, so if the limit of this one equal to L, and L is less than 1, so you can see the an is kind of smaller than the an plus 1, so it's decreasing sequences here, right? Then we will say the summation and n from 1 to the infinity, this an we say is absolute convergent. Right? So that's what we say this is absolute convergence here, because we know by the convergence series, so we know therefore it's a convergence, right? So we know this series is a convergent because we know the absolute convergence will guarantee the convergence here. So then the second part here, we say the ratio test. So here it will be if, so here, this one, here's ratios, not ratios here, all right, so, all right. So now the second one here, we say if the limit n approach to infinity. So if you compare the two exact, to the term right next to each other, an over an plus 1 over an, if this limit equal to L, and this L is greater than 1, that means, this series, right? So this sequence for the series, the an sequence is increasing sequence. Then we know this is what is a divergence here, right? Because this is your sequence get bigger and bigger and bigger. Or if you say the limit n approach to infinity, if when you compare the an plus 1 to an, if this is going to the infinity, now of course, it's kind of obvious we said, and then the series n plus to the infinity, this one is what is a divergence here. So we know this is a divergent series, kind of intuitive truth, right? Because when you get a bigger and bigger, or the ratio is go to infinity, that means you add up going to be the infinity. Okay, so the third one here, this is the one sometimes will give us the trouble. So if the limit n approach to infinity, if your ratio from the an plus 1 to the an, if this one here is equal to 1, okay, so be very careful. If this is equal to 1, then we said, okay, so we know the ratio test, is inconclusive. That means I cannot decide, not decide, that means I cannot decide if the series is a convergence or divergence here. So we might need to find a different method to check it. Okay, to personal, I think a ratio test is very, very handy, especially you have like exponents and if you have the factorial and those things, the ratio test is, provide a very good form for us to do the tests here. So let's take a look at some examples here. So the first ones here is that determined is this one is convergence or divergence by ratio test. So let's take a look here. So we say the an plus 1 to the an, right? So let's see what is the limit this number approach to. So this one is the limit n approach to infinity. So what is the an plus 1? That means you replace n with n plus 1, right? So this is 4, the n plus 1. Then the an will just be n and the 4 to the n. So you have the absolute values here, okay? And then because all these values are positive, so this absolute values really does not make any differences here. So this is n plus 1. This is 4 to n plus 1 over n to the what? 4n's, right? Then you have a two fractions. So what I need to do is here, I need to flip it, right? Okay, so this is n plus 1, then times the n, this is the 4n's here. Okay, so you flip it, then maybe you can simplify it. So this is 4n and the 4n, this cancel. So this ones here will be equal to limit n approach to infinity. So you still have a 4 here, right? So you will have a 4, and then you have n plus 1 to the n, right? So now this one, so you can take the 1/4 out. So this is limit n approach to infinity. This is n plus 1 to the n. And we did this many times because the n plus 1 and the n, they are in the same speed. So what is this ratio going to be? This ratio going to be equal to 1, right? So the whole thing, this is equal to 1/4. So this is less than 1, right? So I know this series here, n to the 4n, is what? Is a convergent absolutely by what test here? By the ratio test. Okay? All right. So now let's take a look at the second one here. So the second one, this is the alternating series. Like we said here, let's try to see by ratio test. Okay, so I said the limit n approach to infinity. So the an plus 1. So the an plus 1, that means this is n plus 1 to the factorials, right? So this is -4 to the n plus 1 and divided by n factorial. This is -4 to the n. And because this is the absolute value, so I can get rid of this negatives here. So my top here will be n plus 1 factorial, and I can treat this as like the 4 to the n plus 1. So the same things here, this is n factorial, this is the 4 to the n. Because you have an absolute value, then the negative in front, it doesn't matter anymore. So now this one's here, I can flip it. Okay, so this is a 4 to the n plus 1. And the times, this is the 4n and the n factorial. So the reason why I mentioned a while ago, I said the ratio test is extremely good for the factorial. Take a look here. This one, 4n plus 1, I can say is 4n times 4, right? Then the n plus 1 factorial, what is, I can simplify the n plus 1 factorial. It's n plus 1. Then the factorials, right? Then here, this is the n factorial, and it's 4n. So here, now take a look. We can cancel a lot of things. 4n cancel. n factorial, we cancel out. So I have this is the limit n approach to infinity for the n plus 1. So what is this limit going to? Because the n plus 1 is on the denominator. So this limit is going to approach to what? Approach to 0. So this is less than 1, right? So what is the based on the ratio test? So what do we say here? So we say n from 1 to infinity. This n factorial, this is negative 4 to the n. What type of here? This is what? Convergent, what? Absolute, right? So this is a convergent absolutely by what? By the ratio test, right? If it's a convergent absolutely, then we know this one is a convergence here, right? Because by the convergent series we learned in the previous lectures, if it's convergent absolutely, then it's a convergent. Okay, now let's take a look. This one's here, all right? So for this examples here, we say use the ratio test. Okay, so I will say limit n approach to infinity. And so I will put here, this is the n plus 1 to the cube, right? Then this is negative 1 to the n plus 1 divided by n to the cube to the negative 1 to the n. Okay, because this is the absolute value, all the negative sign disappear. So I can just say this is the n plus 1 to the cube to the 1. And the bottom is n cube to the 1. So I can say this one is the limit n approach to infinity. You flip it, right? Okay, so in here, take a look. Here, this is n to the cube roots, and this is n to the cube roots. And they are running the same speed. So we know now what is the limit will just be the coefficient in front of it, right? So it's 1 over 1. So it's 1, right? So it's 1. We say, oh my gosh, it's 1, right? So I can make the conclusion by what? I cannot make a conclusion by ratio test. So I need to find a different way to decide if this is a conversion or divergence here. Okay, so the first thing is here, right? So the ratio test is not helpful. Now I see this is the alternating series. Okay, since this is alternating series, then I will say limit n approach to infinity 1 over n cube. So what is this limit going to be? This limit is going to be 0, right? So if this limit is going to 0, then I know this is n from 1 to infinity. This is negative 1 to the n. This is n to the cube. So this one is convergent. Why? By the alternating series test. Okay, so this one is the convergence, right? Okay, so now let's take a look to see is absolute the convergence or not, right? So I will say if it's absolute convergence, that means I'm testing n from 1 to infinity, absolute value, negative 1 to the n and n to the cube. So this one is equal to n from 1 to infinity. So it still is n to the cube roots. Okay, so now I know the n to the cube roots. This value is going to be greater than n from 1 to the infinity, 1 over n. Correct? Yeah, because this one's here, right, is smaller than this one here, right? And then we know, then we know this series This is what type of the series? This is a divergent series. This series is a divergent. Why? It's by harmonic, right? Because this is a harmonic series. So harmonic series is a divergent, and this series is greater than harmonic series. So I know what happens here. So I know this series is a divergent by the comparison test. Correct? Because if you are greater than a divergent series is divergent. So this is divergent. Because this is divergence, right? So what? So because this is a divergence, so that means what? That means the summation n from 1 to infinity, the -1 and square root of n cube is what? Is not absolutely. It's not absolutely convergent here. Okay, so now let's compare what do we have here, right? So in here we said, okay, this series is a convergent, okay? And in here we say this series, the same series is not absolute convergent, right? So by combined these two, right? By combined these two, so what is the the results here? So we say this series -1 to the nth power n to the cube. So what do we say about this series? This series of what is a converging what? Conditional. Correct? Right? Because that's what, so for this one is a very interesting one. So first we use the ratio test. And we say, oh, the ratio test is inconclusive. We cannot make a decision. Then we say, okay, so what do we do? So the second thing is here, this green ones here, we use alternating series test. Then we find that this is convergent. Then the blue ones here, we say, let's take a look of whether this is absolute convergence. So I put the absolute value, then compare to the harmonic. So I say, hey, this is a divergent. So I know if because it's a divergent, so we know this series is not absolute convergent. So combine the green one and the blue one. So I know this series is convergence of what? Conditional. Okay. All right. The last example is also very interesting. So this is the form we call the recursive forms, right? So I want to see if this series is it's a convergent or divergent, but they did not even give us the exact forms there. So we say, okay, I'm using the comparison series. I'm using the ratio series. This is another thing. So the ratio series is pretty handy here if you have a recursive forms here. All right, so now I will say this is a limit n approach to infinities, right? An plus 1. So what is an plus 1? So this is the 3an, 2n plus 1. Now here is an, right? Okay, so now in here, because it's the A1 is 4, AN is the 3n, so we know it's all positive number. So I can remove these absolute values, right? So this is 3an, this is 2an, this is an. Now I flipped it. Okay, so after I flipped it, now you say, oh, this is an and an cancel, right? So the an and the an cancel. So what I have here, I have a limit n approach to infinity, the 3, the 2n plus 1. And because I have an approach to infinity, so this one approach to infinities, right? So the whole series will whole limit will approach to 0. Because this is the 0 is less than 1. So I know the summation n from 1 to infinity, this an is what? Is a converging what? absolutely, right? By what? By ratio test, right? So because this is absolutely convergent, so that applied, this is the what is a convergent series, right? Because it's an absolute convergent, it will be the convergent series here. All right, so that is the what we call about the ratio test. Like I mentioned, my personal the ratio test is my, I like this test very much because I say it's pretty good to handle, especially you have the like the factorial, have exponents, and it's easy to find the limits here. The only thing here is if the ratio is equal to 1, then you might need to find, so it's inconclusive, and you need to find other method, try to test the series is a convergent or divergent. All right, that's it. And so our second video, we're going to talk about the root test, okay, to decide a series is convergent or divergent here. Okay, nice talk to you. Have a good day, and I'll talk to you in our next videos. Okay, bye-bye.